morning, everybody. My name is Anja, Petković Komel. It's Anja, so it's spelled with a J, but you can imagine a Y there, and then you'll know how to pronounce my name. So I heard this podcast where they told you're supposed to say in the first 5 seconds to get people's attention what you want to do, otherwise they will just look away. So what I want to do with this lecture is try to help you understand some of the error messages you get when you're trying to prove things with a proof assistant and get super stuck. And then you're like, I don't know what the hell happened, and I don't understand the error message. And actually, the type theory is the logic behind, and some of the error messages are referring to that. So this is introduction to type theories, and this is what we're doing. So let's get into it. First, why type theories, right? So I'm a mathematician by training, and the answer for mathematician is because they're beautiful mathematical foundations that can express a constructive approach. Right? Very romantic. And the answer for the rest of the world is because proof assistants are built on them, and we want to use the proof assistants. Right? Now, I used to be in this first category where I thought they were beautiful and that was enough for me. But more and more, I'm in the second category when I'm just trying to use the proof assistant, and then I really appreciate if I know why it doesn't work. Okay, so basically the question is then why proof assistants? And we tested the audience a little bit yesterday, so can we have a raise of the hand? Like if you have ever used a proof assistant before, please read. Okay, so most people here. Obviously, I'm preaching to the choir today. Now, please raise your hand if you use the proof assistant for more than just trying to learn the syntax. Almost everybody. Good. Okay. Now raise your hand if you got really stuck at some point and you didn't know what was going on. Yay! You came to the right place. All right. So since I'm preaching to the choir, you will not appreciate the next slide, but I will include it in anyways. So why do we want to use proof assistant? So it's to verify software correctness, right? That's the answer for the computer scientists in you. And there's the canonical example is, the Ariane 5 rocket. It was launched on June 4th, 1996, and about a minute later, it kind of looked like that. So this is the canonical example. It was a numerical error, and then, things went down. And the reason I'm including this example is because software correctness verification is expensive. It's expensive with resources. You have to have, at this point, a lot of expertise. We'll see what AI will do. I'm curious, but we're not going to do it for all apps that are out there. We want to do it for the ones that count, right? And the ones that count are, the ones that are very expensive, right? And the ones that, are very dangerous. Like, I don't know, if you're getting LASIK surgery, right? You want that laser to point to exactly the thing it's supposed to point and not anywhere else in your body, right? Otherwise it's dangerous. Or, if you're launching people into the space, you would appreciate if they came back alive. And, these parts of software, I think, is valuable to be verified. Okay, so it's actually quite active research area. So it's being used for example, verifying smart contracts, formal verification of a compiler. So this is one of the most famous ones. It's the ComCert. ComCert compiler. We have a formally verified file system. So the things that are either expensive because they're dangerous or because they get used a lot. So a compiler gets used a lot, and if you verify the entire compiler, your bug is not in the compiler; it's somewhere else, and that's very valuable. So this is worthwhile for you. And there's also a lot of conferences. mathematical examples first. So we have the formal proof of the four-color theorem. Who has heard of the four-color theorem? Everybody? Okay, I don't have to explain it. Yeah. So it was first done with a computer, and then it was formally verified in this in microphone. Mine turned up. It's back. Hello. Then we have a machine check proof of the odd order theorem. So another big theorem that was machine checked, and then if you go to Lean, this isn't working. Maybe I've got the portable one. So the proof assistant Lean has a big library of formalized mathematics already, and this is, I think it's a bit of an old slide, but it's more stuff there for sure at this point. So it's pretty active in what we're doing. And nobody will hear me if it's down here.
Lower. Right.
Technical issues? Doing a formally verified microphone? I wish. All right, so like I said, active research area. So there are quite a few conferences there. Questions?
Yeah, we can't hear.
Yeah.
Yeah, it's all right. Coffee break? Do you have another microphone, or do I just shout?
Lena is checking now with the
Okay.
technical guy.
So how loud do I have to be for you to hear me?
I think you can hear it. We can kind of hear you better when you're near that
This
mic.
guy? Ah.
Well, maybe you can repeat
Another alternative. This will mess up my plan to walk around, but I'll do my best to be the clown from the fixed point. All right. So there are quite a few conferences that deal with this. So one of them is the Certified Programs and Proofs. And then you have, the subject areas, and, logic and verification is quite big there. And also type theory is quite big there. If you see the red one. Program verification, formal software verification. So it's, it's happening. Then you have interactive theorem proving conference, also very active. Then you have types. So some of you have probably been to some of these before, but I'm just, I'm trying to sell you type theory, so this is part of my sales pitch. Okay, so who has heard of this guy? Almost everybody. Okay. No, for the 5 of you who haven't, I was unfortunate enough not to meet him, and I would love to. But I like his story, right? And Vladimir Voevodsky, he was a very good mathematician, originally from Russia. He got a Fields Medal, so that's like mathematics equivalent for Nobel Prize, so like super smart. And he was doing some algebraic geometry stuff. And then what happened to him was that he published the wrong result, right? And then, first of all, nobody found it, the problem, for a long time. And second of all, when they did, he didn't believe them for a while. Until years later, he finally figured out that they were actually correct, and then he was like, oh my God, I was so convinced, and nobody else would believe the other guy, because I'm a Fields medalist and he's, a nobody, quote unquote. So he was like, okay, humans shouldn't do peer reviews for mathematics, at least not the proof checking part, right? the computer should do it for us, because there's a problem with, I have too much authority in my field that whoever gets to review my paper, if they see my name on it, they'll be like, oh, Vladimir is probably right, I'm stupid. So that's one problem, and the second problem is you just miss something. We're humans, we have time constraints, we have, bad days, good days, or, it's just, we're all indoctrinated in the same way of thinking that nobody finds out the error. So then he got really invested into this, proving with a machine, proving with computers, and I think at that point when he got invested in it, it sort of, got more traction and people started appreciating it more and more people got involved, and then it sort of, snowballed from there. So I really like his story, and I, like I said, I wish I could have met him. Okay, proof assistance. The point of this slide is there are many. So one is Rock, this orange bird here, and that's the one I made you install and download if you haven't already. And it's based on a type theory called the calculus of inductive constructions, or some more advanced version of that. Then you have Agda, which is based on Martin Löf type theory, something Brigitte has mentioned already yesterday, and we will talk a lot about today. Then we have Lean, and it's also based on basically the same type theory as Rock. And then you have another version, so in Agda you have this dash cubicle, which gives you a cubicle type theory. And then,
that works?
Well, I can't move them around, but it works in principle. Okay.
I'll take a look.
So enough minutes for a coffee break?
No coffee. Coffee break without coffee.
Well, this one was plugged in and it still is turning off. Yes, but it was plugged in when I took it.
Yeah, but it's still red.
Yes.
It's not charged.
Okay.
So use that for now.
All right.
After lunch, you should be charged.
Okay.
Sorry.
So apparently my exercise is coming after lunch. Okay. Thank you so much.
Yeah.
All right, and then we have, so Rock can also be, improved with HOS, homotopy type theory. So it used to be a separate library, and now I think it's just, you can just, it's part of the standard library already, you can just switch it on. And then you have Unimath, which has univalent foundations, and so on and so forth. And these are not all, there are more proof assistants with more type theories. And some of these have been around longer than the others, so we have some, cubicle type theories, some, higher order logic, we have computational type theory, we have extensional type theory, and we have something called general type theories here. I included that one because I was one of the people who developed it, so I thought it was, suitable that I tell you what that is out there. And it's sort of designed to, include your own type theory and work with the one that you want. That's sort of the idea behind it. Because, the selling point is there are many type theories, and that's why my lecture is titled Introduction to Type Theories in plural and not just one type theory. Incidentally, I will mostly talk about just one type theory, but I will try to, point you to the direction in which you can extend them or change them, and hopefully you will understand why there are many and how there are many. All right. So this slide is probably redundant now. Why are we learning about type theories rather than using a proof assistant at this lecture? Well, because when you use a proof assistant, you kind of look like this most of the time. And some of these situations I hope to alleviate. So please bear with me. Here is the approximate, my idea of how the lecture should be structured. So we will start with Martin Löf type theory. So it will follow quite closely the chapter 1 of Egbert Heike's book, Introduction to Homotopy type theory. So just the chapter 1, you don't have to read the whole book, you can if you want. Why I chose Martin Löf type theory out of all of the other ones is because I personally think it's the easiest one to understand, and it has a good textbook, and that's really helpful if you're trying to understand something. So then we would look a little bit about the differences between MLTT, so Martin-Löf type theory, I'll use MLTT, and the calculus of inductive constructions, and we'll do ROC. So what we want to do here is interactively prove some very easy theorems, and mostly I just want to show you how all of these principles from the theoretical side apply to a proof assistant, right? And I think, teaching you how to use a proof assistant and how much fun it is to use a proof assistant, which it is, could be a whole other lecture and a whole other course, just that. But usually, when people say, oh, I want to learn how to use a proof assistant, they start by doing, which is great, but then they get stuck because, they don't have the basis. So I'm giving you the basis and then I'm pointing you to the direction of where you can find it. And if you want to learn how to use a proof assistant, you should, advance and attend another course or a lecture or an online tutorial or something. So I'm just trying to set your expectations quite low. Why have I chosen ROC? Well, the most natural one would be Agda because we're doing Martin-Löf type theory. But I chose ROC because, in my personal opinion, out of all of the ones I know, it's the easiest one to install. And I didn't want to have like a 5-hour install party for 1 hour of lectures. So, but the principles, how they use type theories, are kind of portable between all of them. Otherwise, Agda or Lean might even be better choices for the purpose of this theory. So I plan to do a bit of live coding and have a few slides so you can follow along. And then, if time permits, for the last lecture, I might see how we progress, or I might let you choose. We could do more, proving in ROC, or we could visit some meta theory of type theories. So, when I said Andromeda 2 is a prover that implements sort of general type theories, well, I could tell you, precisely what I mean by that. So, what is a proper definition of a type theory, and how the rules look like, and how do you pose them? So, this is something to be decided later. I'm just including it here. All right. A very important disclaimer for today. We will discuss type theories only syntactically, okay? This is how I think of type theories, and this is how I think of type theories in a proof assistant. There's a whole lot of research about semantic models of type theories. And if you're interested, ask for references, or even better yet, next week Paige is coming. She's doing the category theory, and she knows much more about it than I do. So I would just point you in her direction if you're interested in that. Knowledge of category theory is kind of a prerequisite to understand what that is. But if somebody comes asking me questions about the semantics, I'm just going to go like, no, ask Paige. I know something about it, but she's a much better expert among the lecturers here. All right, any questions up to this point? Good. All right. No more slides from this batch. So hopefully this works. Yeah, we will go straight into Martin-Löf type theory. Okay, so one of the type theories. And for today's lecture, and probably all of tomorrow's lecture, we'll be just talking about Martin-Löf type theory. Okay, so Brigitte did a great job preparing the terrain for me yesterday. So we already know about the Curry-Howard correspondence, and now I will formally introduce all of the rules of Martin-Löf type theory and how they look like, right? Especially equalities that she generously let me do it. All right, so in Martin-Löf type theory, every element comes equipped with a type, okay? So in set theory, you can say something like there's an element that belongs to a set or not. In type theory, you can't say that. If you're talking about an element, it's already, you know what type it is. Okay, you cannot talk about an element without knowing its type. And type theory is a deductive system, and the inference rules, they make the derivations, okay? So I will be very specific about what I mean by this in a little bit. I will let you have the slides later, in case you're afraid this is just gonna go off. So we derive judgments, okay? And Brigitte already introduce judgments, but I will tell you what they are in Martin-Wolf type theory. Okay. So the inference rules look kind of like this. We have hypotheses on the top of the line and then a conclusion on the bottom of the line. And just, for the future reference, I basically screenshotted this from the textbook I told you about, right? One, because then I can use the same notation. Second, because I'm lazy and somebody already did all of the work to make all of these rules look nice. But one thing is that there is a dot here that it sometimes is there or not. It depends on how the sentence before it went into the textbook. So if there's a dot or a comma or something, just disregard it. It's like, a side product. But you will appreciate me at some point. If you're reading the textbook, it's going to be exactly the same shit. So here's where my laziness pays off. All right. So this is how inference rules look like. And then an example of that is an inference rule for function types, which kind of, can look like this. If I have an element, a, little a of type big A, and I have a function from A to B, then f applied to this A is of type B, right? So you've seen some of the inference rules yesterday in big derivations, so this shouldn't be too surprising for you. Okay. These inference rules, these guys here are judgments, right? And there are actually 4 kinds of judgments in Martin-Wolf type theory. There is a well-formed type judgment, so we say A is a type in context gamma, so these gammas here are context. And then we have the well-formed type judgment, and then we also have a judgment that 2 types are judgmentally equal. Okay? And I'm going to use the word judgmentally equal a lot today because there is going to be something called propositionally equal tomorrow, and they're not the same thing. Okay? And you can see that we're using this equals with a little dot on there is because we want to differentiate between these two. And the propositional equality for tomorrow is the one that we really want to call equality. And this one, some people call definitional equality, or we're going to call it judgmental equality. It's slightly different, okay? So just to be clear, this dot here is on purpose, unlike, these dots that are not. All right, then we have a well-formed term. So little a is of type big A, and this is, a well-formed term, little a. And then we have judgmentally equal terms, A equal dot B, and we have to know of which type because they're terms, right? So if I have terms, I cannot say without knowing what their types are. So also this means that little a and little b have to have the same, exactly the same type. Question?
I was going to ask if A is the type of A and B, or if it's the type of the equal signs.
This is a good question. This is the type of little a and the type of little b. Okay? This judgment, like this equality judgment that has no type, it's an equality, right? Okay. So terms have types, equalities have no type, okay? But A and B have the type, and this is like a syntactic part of the judgment. Very good question. Yeah?
Can be like A equals dot, or big A equals dot, big B, or the term equality. Can those appear inside gamma as well?
No.
Okay.
Excellent question. I will explain what gamma is on the next slide. Yes. More questions? No. You can just shout when I don't see you. You can just shout there's a question, and I will stop. Right, so we call this gamma a context, and we call these 4 kinds of judgments, like what's on the right-hand side of the turnstile symbol, we call them judgment theses. Okay? So when I want to say something about all 4 judgments kinds at the same time, I'll say, oh, it's a judgment thesis, and you don't know which one. But, some things sort of transport from one judgment thesis to the other, one type of kind of judgment to the other. Okay. Contexts, okay? Contexts are finite lists, so a finite list of stuff like this, and unlike Brigitte yesterday, our contexts are ordered. And they have to be ordered because they're kind of dependent, okay? So a context is a list of stuff, so here you have x1 of type A1, and then x2 of type A2, but this A2 can involve stuff about x1, sorry. So this A2 could be dependent on x1, okay? And so on and so on, and like xn is of type an, but this an can be dependent on all of the stuff that came before it. Question?
Yeah, this may be that question, but is the relationship between the context and something like a telescope?
I don't know what a telescope is. I mean, I know the thing that you look at the stars with, but I'm pretty sure that's not the thing that you're referring to.
Yes, that is correct. This can also be called a telescope.
Ah.
But then you probably do these double dots and just shorten this notation.
Thank you.
But this means roughly the same thing.
Okay, thank you.
All right, thank you. See, we have an expert in the audience. Knows better than me what a telescope is. I was never much of an astronomer, you know. All right. So, additionally to this being a list, right? It has a property that, you know, the next type has to sort of be well formed if we have the context of fewer things, right? So here for every k, if we have the context up to k minus 1, the type ak dependent on these little x's from 1 to k minus 1 has to be a well-formed type with regards to these x's, okay? So for us, this is a context. Okay, and because we're already talking about the dependency, I clicked, and now it's not working. Right, we have a context of length 0. It's called the empty context. We have, you know, a list of length 0, and this is where you start from building your judgment, where you start building your judgments from. And then, because I was talking about a dependency, in Martin-Löf type theory, it's a dependent type theory, and the dependency is really important. So we have dependent types in terms, okay? So we have a dependent type family, so we write it like this. B depends on X, is a type, and it's a dependent type theory because it depends on X. Incidentally, it can also depend on all of the stuff from gamma, but sometimes we want to emphasize that it, you know, maybe it only depends on X, and then we'll say B depends on X, or maybe we want to emphasize that it depends on X because that's the important stuff that we're going to do something with. Okay. Technology. Not verified software. I don't know what's happening. It's playing tricks on me. Good. Okay. Go again. Okay. So here is an example, right? We could have something like, in context where we have a natural number, little n, we could say that a vector that contains natural numbers is of size n is a type. Okay? So here I'm using parentheses for sort of dependency or application, and here I'm not using parentheses, and I'm not going to really be consistent with that. So if you're confused, this is kind of like function application, right? I apply type constructor vec to the type n and the little n kind of thing. And this is a dependent type family on little n, which is a natural number. And then we can have something called a section, and a section is like a dependent term, okay? So we have in context gamma, and we have x of type A, and we have little b of x is of type big B of x, and it's a section. Okay? So why do I call this a section? Maybe I can draw a picture. So, hope people can see this. So, I imagine this type family as sort of like a square above a line that is type A. And for every little x in A, I have a section b of x, and it's like a whole line here, right? So this is sort of like a mathematical picture why we call this a section. But you can think of it as a dependent term. We have dependent types and we have dependent terms. And we can call them sections if we want. And an example of a dependent term would be, here we had an example of a dependent type. So vector, and the size of the vector is the dependent thing, right? And then a dependent term of this type would be, well, I can have n many zeros, right? And n is in the context here, right? So we can have a dependent term because the size of this vector depends on n, and I'm just gonna, put n many zeros here in the type. Right.
Anja.
Yes.
Question. So is the rectangle meant to represent like the set of possible inhabitants of that term?
Yes. Exactly. The rectangle is supposed to represent all of the elements of the type family. Yes. Thank you. Okay. And now we're going to do inference rules. Oh, just keeps getting better. We're going to do inference rules. Now, I know this might be a little boring because we're just going to see a lot of inference rules. But you can think of them as, do you guys know what a herbarium is? Who knows what a herbarium is? Not many people. You're so young. Okay, see, I'm older than Google. Before there was Google and fast internet and stuff. I mean, when I was young, we still had a computer and had this floppy disks thing that people joke about. But we just spent a lot of time outside because it was just so slow and just burned your nerves. So what we did in our free time was we collected like plants from the nature, and then we dried them and then stuck them to pieces of paper, and then you made a book, and that's called a herbarium. It's like a systematically ordered dried plants, right? And then you could learn what like a leaf of a maple tree looks like, right? That was how do you learn about what plants there are? Well, you see a big book of dried stuff, and then you look up the names, and then you go into nature and try to find them, right? Alternatively, you could try to find them first and then look them up, right? This is how you digital age people do it, right? You have an app that scans, you take a picture of the plant and then you ask AI, what is this? And then it tells you it's a maple tree, right? We had to, do the other way. We had to do the book thing. And these inference rules, because I'm very old apparently, I'm gonna present these as a herbarium kind of thing, right? I'm gonna show you all of the rules of Martin-Löf type theory systematically, because I just don't have enough time for you to go out and see them yourself, right? The alternative would be that I give you a big proof written in rock, for example, and then we go through it and like on the fly I explain the rules to you, but there's no way it's going to be presented in a way that is, understandable and that you can follow it. So I chose to do it the old-fashioned way. But, I make a promise to you that, it will all start to make sense once we can start making the derivations, and once we see how the proof assistant is really